Welcome to our very first lesson in this course. Today we are laying the foundation by exploring how data management evolved from simple file systems to the sophisticated databases that power modern applications. Imagine your next micro SaaS idea of 2025. How would you store information like user profiles, posts, or any interactions? The choices you make to manage your data will impact everything from performance to availability, from security to future scalability. That's why understanding database fundamentals is paramount. Let's have a quick look at this lesson's agenda. First, we'll talk about the data evolution from manual file management to structured databases. Second, we'll brief nearly 60 years of database history. Then we'll move on to today's database ecosystem and some criteria of strategic selection. And finally, we'll quickly present some real-world implementation patterns. Let's start with a fundamental question. How did organizations manage data before databases? Imagine a small business in the 1960s maintaining customer records. Each customer's information would be stored in paper files, later digitized into separate computer files, perhaps text files or spreadsheets. Early digital storage used simple file systems, essentially electronic filing cabinets. Each department might maintain its own customer files, inventory sheets, and transaction records. While this works for small data sets, it quickly becomes problematic as businesses grow. Think of a library trying to manage books, members, and loans using separate spreadsheet files. Every time a book is borrowed, librarians would need to update multiple files manually. Databases fundamentally differ from file systems in several key ways. Data independence. Applications don't need to know physical storage details. Concurrent access. Multiple users can safely access and modify data simultaneously. Data integrity. Relationships and constraints are enforced automatically. Structured query language, standardized way to interact with data. Consider a bank's ATM network. When you withdraw money, the system must instantly update your balance, maintain transaction history, and ensure no double spending while handling thousands of concurrent transactions. The transition to database was driven by critical business needs. First, data redundancy. The same information was duplicated across multiple files. Second, data inconsistency. Updates to one file didn't automatically reflect in others. Third, data security. File systems offer limited access control. Finally, data recovery. No built-in mechanism for backup and point-in-time recovery. Let's establish some fundamental terms you use throughout your database career. A table is a collection of related data organized in rows and columns. A record, row, or tuple is a single data entry in a table. A field or column is a specific attribute in a table. A schema is the structure defining how data is organized. A query is a request for data manipulation or retrieval. These terms form the foundation of database communication. Just as architects need a common vocabulary to discuss building plans, database professionals need these terms to effectively collaborate on data solutions. PostgreSQL builds upon these fundamentals, adding powerful features like custom data types, table inheritance, multi-version concurrency control, and the list goes on and on. We'll dive deep into these PostgreSQL specific features in section 3, but first let's understand how database systems evolve to their current state. Let's explore how databases evolved from simple hierarchical systems to today's sophisticated platforms. This journey mirrors the increasing complexity of data management needs in computing. In the 1960s, IBM developed the first major database system, the Information Management System, IMS, for NASA's Apollo program. IMS used a hierarchical model organizing tree-like structures where each record had a single parent. While revolutionary for its time, it had a significant limitation. Representing many-to-many relationships was extremely difficult. Everything changed in 1970 when Edgar Codd published his paper on relational model. Instead of rigid hierarchies, data could be organized in simple tables with relationships between them. The relational model's power comes from its simplicity. Just as basic shapes can create complex art, simple table can model complex relationships. In the early 2000s, companies like Google, Amazon faced unprecedented data scaling challenges. Traditional relational databases struggle with handling massive data volumes, scaling across multiple data centers, providing flexible schema designs. This led to the emergence of NoSQL database, each optimized for specific use cases. Let's have a look at them. Document store for flexible schemas, key value stores for simple, high-speed operations, graph database for connected data, column family stores for wide-scale analytics, and so on. Today's landscape combines the best of both worlds. New SQL databases like CockroachDB and modern PostgreSQL implementations offer ACID guarantees of traditional database, horizontal scalability of NoSQL systems, advanced features like JSON support and vector operations, which is becoming more and more popular in RAG AI agents. If you don't know what ACID means, don't worry. We'll introduce this concept in the next lesson, and we'll dive really deep into it in section 5 when we cover transaction management. Let's explore today's database ecosystem. The landscape has evolved significantly from one-size-fits-all approach of the early 2000s to a rich tapestry of specialized solutions. Modern database systems generally fall into 5 main categories, each optimized for a specific use case. First, relational database, the backbones of transactional systems, handling structured data with complex relationships, perfect for financial systems, ERPs, CRMs, and any application requiring ACID guarantees. Document stores, optimized for semi-structured data like user profiles, content management, and catalogs. They excel when data naturally fits a hierarchical model or document-like structure. Graph databases are designed for heavily interconnected data. Think social networks, recommendation engines, and fraud detection systems. Time series databases are built for handling temporal data, for example, from IoT devices, monitoring systems, and financial markets. Vector databases, the newest category, are specifically designed for AI and machine learning workloads, handling similarity searches and embedding storage. In 2025, each category has established leaders. Relational, PostgreSQL has emerged as the open source leader, competing directly with Oracle and SQL Server in enterprise deployments. Document, MongoDB probably maintains its leadership, while CouchDB serves specific high availability use cases. Graph, Neo4j dominates specialized graph workloads, while PostgreSQL with its graph extensions serves hybrid needs. Vector, Pinecone leads the pure vector space, though PostgreSQL vector extensions are gaining traction for hybrid deployments. What's particularly interesting is how PostgreSQL has evolved to handle multiple paradigms effectively, making a versatile choice for many organizations. Several key trends are reshaping the database landscape in 2025. AI integration. Databases are increasingly incorporating AI capabilities, from query optimization to automatic index management. Hybrid deployments. Organizations are combining different database types to handle varied workloads. Edge computing. Database systems are adapting to run closer to data source with improved sync mechanism. Serverless database. Automatic scaling and pay-per-use models are becoming standard. DBaaS has become the default deployment model for many organizations. Key developments include managed services. All major cloud providers now offer PostgreSQL as a managed service, handling maintenance, backup, and scaling automatically. In the coming lectures, we'll not only cover how to locally install PostgreSQL, but also how to spin up PostgreSQL instances in the major cloud providers. Serverless options, pay-per-use models with automatic scaling are increasingly popular. Multi-cloud, database services that can run across multiple cloud providers are gaining traction. This evolution reflects a broader trend. Databases are becoming more specialized while simultaneously offering more flexible deployment options. Understanding these trends will help you make informed architectural decisions for your applications. Selecting the right database for your application is a critical decision that impacts everything from development velocity to operational costs. Let's examine the key factors that should guide this choice. When evaluating database systems, reconsider these fundamental aspects. Data structure requirements. How structured is your data? Does it follow a rigid schema or need flexibility? Access patterns. Are you doing more reads or writes? Do you need complex queries or simple key value access? Scale requirements. What's your expected data volume and user concurrency? Developer resource. What's your and your team's expertise and capacity for database operations? Modern databases often require balancing between performance and consistency. Strong consistency means every read receives the most recent write, but may require more coordination and higher latency. Eventual consistency means that the system may temporarily return stale data, but offers better performance and availability. Let's look at strong consistency examples. Banking systems. When you withdraw money, the balance must be immediately consistent across all bank branches and interfaces. Airline booking. When booking the last seat on the flight, the system must guarantee no double booking occurs. Stock trading. Stock prices of available shares must be strongly consistent to prevent arbitrage opportunities. Now for eventual consistency examples, we can find social media feed. When you post a status update, some followers might see it immediately while others see it after a delay. Product reviews. When you submit a review on an e-commerce site, the average rating might not update instantly. Content delivery networks. When you update a website, different geographic regions might see the changes at slightly different times. As systems grow, they will need more capacity. This is usually called vertical scalability, which is basically adding more powerful CPUs or more memory. However, vertical scalability has narrow physical limits. Modern applications often require what we call horizontal scalability, which is when we add more machines to handle load. While raw performance numbers are important, remember the best performing database that loses your data is worse than the slower one that keeps it safe. Let's examine real companies and how they solve their database challenges. Instagram, for example, uses PostgreSQL for user profiles, photo metadata, tags, and etc. Cassandra for the photo feed pipeline, Redis for the activity feeds and session management. So they handle over 1 billion users. Twitch's engineering team revealed in their 2016 infrastructure post that PostgreSQL handles their most critical workloads. What makes Twitch's implementation remarkable is their original central database cluster, which in 2016 handled over 300,000 transactions per second. Let's conclude with a quick thought exercise. Imagine you are building a ride-sharing application. You need to store driver locations with real-time updates, user profiles and payment details, trip history and receipts. Think about which database types you choose from each component. I know it's a bit too early for that. We'll discuss this architecture in details during section 3. Where you see how PostgreSQL can handle many of these requirements. Today we've covered the limitations of file systems that database solve, 6 years of database innovation cycles, 2025's specialized database ecosystem, strategic selection framework, real-world implementation examples. In our next lecture, we'll dive deep into relational fundamentals, the core of PostgreSQL's power. As you progress, you'll see how PostgreSQL's extensibility lets it compete in areas dominated by newer databases. The foundation we've built today will help you make informed architectural decisions throughout your career.